Hi students, this is Shivakrishna, working as a assistant professor in civil department at Anurag Engineering College. Previously, I am explained about the unit 3, that is comes under plastic analysis, and what is the design of laterally supported beams, and what is the section modulus, and how to do the design in that particular plastic analysis, and what are the types of sections, that section how to it's classified. This all are learned in the third unit. Next, coming to fourth unit, this is totally explained about plate girders. What is meant by plate girder? It is a type of beam. It carries a heavy loads on that particular structure, and so many vehicles passing on that particular bits. On that situation, they have to maintain the greater loads acting on that particular location. So we have to decide on that particular load and what type of load acting on that particular situation, and how to design on that particular beam, and which type of sections you have to consider on that particular section, and what is the flange of that section, and what is the thickness of that section you have to consider in the design. And in the plate girder, some of the types of plate girders will be included, that is unstiffened plate girder. Here one web plate is considered and one flange plate will be considered. In that particular section, simply support we have to assume in that particular location. On the situation, we have to provide the I section. The I section, it is a composition of web portion and flange portion. The combination of these two motions, it should be categorized as a I sections, and channel sections also you have the web plate and flange plates. And coming to second one, transversely stiffened plate girders. In this, the transversely stiffened plate means here we have to provide the stiffness on that particular location. And third one, transversely and longitudinally stiffened plate girders. Here the longitudinal, the plate girder should be provided on that both directions, that is transverse and longitudinal direction. And what type of load should be acting on that particular plate girder? Here some of the capabilities you have to maintain, that is shear resistance of the stiffness girder. In the shear resistance, it is the plays a very important role in the design of plate girder. This is a very collapsible load acting on that particular location. In this we have to checking the pre-buckling behavior on that first stage. In these requirements, the equilibrium, it is an element inside a square wave plate subjected to a shear stresses. It should be resulted as a complementary shear stresses acting on a particular situation. And after that, the based upon that result analysis, we have to find out subjected to principal compression along one diagonal and tension along the others. And this is the planning of that particular load acting on that scenario. Here the load should be acting on the inclination of 45 degrees on that particular location, and this q is the load intensity pressure will be acting on that situation. So this is called unbuckled shear panel, where the buckling phenomena, it is called, what is the meaning of buckling? The failure phenomena will be occurred on that particular I section. The corners of that, the meeting, where the meeting the flange and web plate, in the situation only the failure of buckling phenomena will be considered. In this situation, as the applied load is incremental enhanced plate, it will buckle along the direction of compressive. It should be acting as diagonal. It should corresponding to shear stresses in that plate is critical shear stresses. To find out the critical shear stress by using this formula, that is Ks pi square ai by 12 into 1 minus v square into t by d whole square. In this situation, boundary conditions have to assumed as a simply supported. We have already seen that first slide, that is assuming a beam as a simply supported beam. In that particular situation, the shear buckling coefficients are given, that is the value, it should be depending upon the C by D ratio. Here we are using the two types of panels, that is wide panels and web panels. In these wide panels, we are using the wide panels in that particular scenario. The C by D greater than or equal to 1. For that situation, we are using this formula, that is 5.35 plus 4 d by c whole square. And another one, the web with closely spaced transverse stiffness, that is c by d less than or equal to 1. In that particular situation, we are using the different formula, that is 5.35 d by c whole square plus 4. See the difference between these two formulas. This formula, first formula is used for wide panels and the second formula is used for web panels. And coming to post buckle behavior, the compression diagonal is unable to resist any more loading it beyond elastic critical stresses. Any further increase in the shear stress is supported by a tensile membrane field anchored to top and bottom flanged and adjacent stiffener members on either side of the web. This total state of the stress, it should be web plate may be obtained by a superimposing membrane tensile stresses upon the critical stresses. See here in this figure, the buckling behavior should be representing as the tensile force should be acting on that particular plane, and how much angle should be provided, that is indicated with theta d. This is the anchoring of tension field. See here, one of the figure, live figure. See here, the combination of two members should be joined here. The failure phenomena, the failure cracking should be diagonal shape only. Here we have to visible. And coming to collapsible behavior, when the load is further increased, the tensile membrane stress continues to exert and increasing the pull on flanges. Eventually, resultant stress obtained by combining the buckling stress and membrane stresses reach yield of the value of web, and it should be determined by non-minus yield criterion. See here, when the load, it should be continuously increasing on that particular member, it should be going to collapsible nature. Without warning, it should be collapsible by the increasing of that particular load situation. See here, this is the three phases of tension field actions. First one is the pre-buckling, and second one is the post-buckling, and the third one is the collapse. Here pre-buckling, the angle should be acting with 135 degrees, and here post-buckling, after acting on that particular angle location, it should be expanded by theta, and it should be further you are increasing the load in that particular location, the collapsible phenomena will be occurred on that situation. See here, ultimate behavior of transverse web stiffness. See here, what is the importance of stiffener means, it should be increasing the web buckling stresses, and it's supporting tension field after web buckling, and preventing tendency of flanges to get pulled towards each other. And what is the importance of stiffness means, it should be ensured that maintain straight and restricting to buckling and involving to web panels. See here, ultimate behavior of the transverse web stiffness, we are providing the web stiffness, how to predict the bending occurs on that particular location. See here, general behavior on the longitudinally stiffened girders are the compression zone of the girder. First, you have to consider. After that, the main section of that particular location is web. It should be increasing to buckling resistance of the web portion, and it is predominantly to shear would develop a collapsible mechanism, provide a stiffness remain rigid up to failure. Why? Because here the collapsing is failure phenomena. So in this situation, we are adding the locations, we are adding the loads, it should be up to collapsible limits. Once one of the sub panels have buckled, post buckling tension field develops over whole depth of the web panel, and influence of the stiffness may be neglected. See, this is the general behavior of the longitudinal stiffness girder. See here, the vertical lines, it should be represented as a longitudinal stiffness, and horizontal lines should be represented as a lateral stiffness. What is the importance of the stiffness means, it should be resisted to bending moment, and it should be resisted to transverse movement also. See here, first of all you have to checking the buckling phenomena in the shear point of view. The factor shear force here consider two types of factors, that is one of the design shear force and actual shear force. V less than or equal to Vd. Vd means design shear force. How to calculate that? Vd means design strength calculated as Vd equal to Vn by gamma m naught. What is the gamma m naught means? 1.1. It will be generally taken in the problems that nominal plastic shear resistance under pressure, it will be given by net pressure equal to plastic pressure. How to define that? Plastic stress means AVFYW by root 3. By using this formula, you have to find out the plastic resistance. And see here we have to find out the section classification, that is the section it should be comes under plastic, compact or semi compact. For this phenomena we are already learned in the previous chapter how to check that cross section of classification of that particular beam. So we using the IAS 800 2007. Based on that book IAS standards, we have to find out the classification of that particular section. And next one, tension field method, we are using to find out the shear strength. And what is the shear buckling means? Here we are using the simple post critical method and simple pre critical method. Here we are using the simple post critical method. Vn net shear force equal to critical shear force. What is the critical shear force means? Here two types we have to define, that is lambda less than 0.8. We are using the FYW by root 3, and that lambda value should be maintained as a 0.8 to 1.25. In the situation we are using the another formula, that is 1 minus 0.625 lambda w minus 0.8 into FYW by root 3, and that lambda value should be more than 1.25. We are using the another formula, that is 0.9 FYW by root 3 lambda w square. See here, the graph will be represented as a x-axis should be lambda w and y-axis should be buckling stress. Both values should be combined. This value should be varied 0.8 to 1.25. See here, critical stress. How to find out the critical stress? We are using different formula, that is kV pi square EI by 12 into 1 minus mu square d by dw whole square. These also some of the range will be there, that is the kV value C by D less than 1 or greater than 1. You have to check it out. By using these ratios we are using the different formulas. And the second one, tension field method we are considered, that is another formula, and this formula it should be involved in IAS 800 2007. Based on that IAS specifications, you have to find out the critical stress. And how to find out the minimum web thickness? In this web thickness we have to consider serviceability requirement and collapsible requirement. In the serviceability requirement, d by tw less than 180 epsilon. When it will be provided? The web connection by flanges along both longitudinal edges. And one more is there, that is d by tw less than 90 epsilon. In this situation, web connection is flanged along one longitudinal edge only. By above formula, both longitudinal edges should be using that value, and after that this value should be implemented, and based upon the C by D values only we are using the different conditions. And after that, what is the design procedure? Here the design procedure of the plate girder should be involved. Taking the length by dimension and depth as 15, it should be calculated as the minimum depth provided in the suitable manner. And after that, area, how much area required for that particular location, by using this formula, that is bending moment by Fi by gamma m naught into D. Here check the flange criteria gives as a plastic section, that is Bf minus Tw by 2 and B by Tf less than 7.9 epsilon. And the web thickness of the serviceability 67 epsilon less than D Tw less than 200 epsilon. In this situation we are using Tw greater than D by 200 epsilon. For this situation, We are using the checking of the shear capacity of that web. Already we are discussed in the previous unit, that is shear capacity checking and bending capacity checking. By using these three only, we are using the different manner, but some of that calculations only we have to consider here, that is simple post critical method and tension method, and what is the C by D values, how it will maintain, and what is the safe tension and field calculations, and stiffener like intermediate stiffeners, and load carrying stiffeners, bearing stiffeners, and torsional stiffeners you have to provide on that particular location. That is totally depending upon the loading criteria. The loading should be acting very heavy on that particular location. In the situation we have to provide the stiffeners. The stiffeners you have to maintain the particular drawbacks, that is one is the transverse stiffness, and load carrying capacity of stiffness, and bearing and torsional, diagonal, and tension stiffness. By using these formulas and find out the design procedure to take the supporters and stiffness on that particular location. Okay, thank you students.